Infinity, a concept larger than life, often mind-boggling and counterintuitive, comes with its own set of bizarre rules that defy our everyday logic. From ancient Greek paradoxes to modern mathematical theorems, infinity has a way of turning common sense on its head. In this journey, we'll explore some of the most fascinating and weird properties of the infinite universe. A hotel with endless rooms that is always full yet never full, different sizes of infinity beyond count, an infinite decimal that equals a whole number, a race that requires infinitely many steps to finish, a snowflake with an infinite edge but finite area, and even a way to double something using infinity. No magic, just math. We'll see how Hilbert's hotel, Cantor's infinities, 0.9 repeating equals 1, Zeno's paradoxes, fractal snowflakes, and the Banach Tarski paradox, each reveal the wild rules that infinity follows. The tone will be fun and accessible, with a dash of humor, but always educational. Get ready to have your intuition challenged by the wonders of the infinite. Hilbert's hotel, infinite rooms and strange check-ins. One of the classic thought experiments to illustrate the strangeness of infinity is Hilbert's paradox of the Grand Hotel, often simply called Hilbert's hotel. Imagine a hotel with an infinite number of rooms, numbered 1, 2, 3, 4, 5, and so on without end. Now suppose that this hotel is completely full. Every single one of its infinitely many rooms is occupied. A traveler arrives late at night seeking a room. In an ordinary finite hotel, a no vacancy sign would send the traveler away. But in Hilbert's infinite hotel, the manager smiles and says, "No problem, we can accommodate you." How is that possible? The manager's trick is simple but counterintuitive. She calls every guest and asks them to move to the next room number. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The guest in room 3 to room 4, and so on forever. Since the hotel has no last room, every existing guest has a new room to go to. After everyone shifts, room 1 becomes vacant, as its original occupant went to room 2. Voila, the new traveler checks into room 1. Despite being full before, the hotel found room for one more guest. In fact, a fully occupied infinite hotel can always make space for another guest, or even infinitely many new guests, by this clever rearrangement. This thought experiment shows that infinite sets don't behave like finite ones. If you have a set of natural numbers, 1, 2, 3, 4, and so on, and you add one more element to it, you still have essentially the same size infinity. Mathematicians call the size of the set of natural numbers countably infinite, denoted by aleph null, which is the smallest form of infinity. In equation form, aleph null plus 1 equals aleph null. Adding a finite number, or even another countable infinity of numbers, to a countably infinite set doesn't increase its size. As the Britannica article puts it, infinity doesn't grow, it remains infinite. In Hilbert's hotel terms, even after accommodating new guests, the hotel still has aleph null rooms occupied. The manager's strategy can be extended to welcome infinitely many new guests as well. Suppose an infinite bus of passengers arrives, with passengers numbered 1, 2, 3, 4, and so on to infinity. A finite hotel would be hopeless, but Hilbert's hotel can fit them in. One way is to move each current guest from room n to room 2n, that is, double everyone's room number. Guest in 1 moves to 2, 2 moves to 4, 3 moves to 6, etc. Now all the odd-numbered rooms, 1, 3, 5, 7, and so on, become free because they were vacated, since every original guest went to an even-numbered room. There are infinitely many odd-numbered rooms, so we can put the infinitely many new guests into those. Room 1, now empty, gets passenger 1. Room 3 gets passenger 2. Room 5 gets passenger 3, and so on. After this shuffle, every passenger has a room, and nothing physically broke. We just exploited the strange arithmetic of infinity. In effect, aleph null plus aleph null equals aleph null as well. Infinity added to infinity is still infinity. Hilbert's hotel vividly illustrates how an infinite total can still accommodate more. A system can be completely full and yet not actually full. This highlights that our intuition from everyday finite experiences doesn't directly apply to infinite sets. It's a counterintuitive property that a fully occupied infinite set can be put into one-to-one correspondence with a proper subset of itself. Here, the guests after shifting still occupy all rooms except a subset like room 1. As strange as this is, it's perfectly consistent in set theory. Before moving on, it's worth noting a limit to this paradox. Hilbert's trick only works for certain types of infinity. It relies on numbering and rearranging guests in sequence. If a truly larger kind of infinity showed up, even Hilbert's hotel would be stumped. This brings us to Georg Cantor's discovery that not all infinities are created equal. Some infinite sets are bigger than others. Different sizes of infinity, countable versus uncountable. After digesting Hilbert's hotel, you might assume infinity is infinity. There's just one kind of endless. Georg Cantor, a 19th century mathematician and the founder of set theory, blew minds by proving that there are multiple sizes of infinity. In fact, there's an infinity of infinities. To understand this, we need to compare different infinite sets. We've seen the countably infinite sets, like the rooms in Hilbert's hotel or the set of all whole numbers. Countably infinite means you can list out the elements one by one in a sequence, even if the list never ends. For example, these sets are countably infinite. All whole numbers, 0, 1, 2, 3, 4, 5, and so on, goes on forever. All even numbers, 2, 4, 6, 8, 10, and so on, also never ends, yet we can enumerate them. All fractions, rational numbers, 1/2, 2/3, 5/7, 1/100, and so on. Perhaps surprisingly, even though there are infinitely many fractions densely packed on the number line, it turns out we can list them in a clever sequence so that we eventually get them all, thus they are countable. Countable sets have size Aleph null, as mentioned, the infinity. Any infinite set that can be put in one-to-one correspondence with the natural counting numbers 1, 2, 3, and so on is countable. Hilbert's hotel and its guests are a fun example of Aleph null in action. However, Cantor showed that some infinities are strictly larger than Aleph null. The classic example is the set of all real numbers. Think of all the decimal numbers. Consider just the real numbers between 0 and 1. This includes 0.1, 0.01, pi minus 3, approximately equals 0.14159. The square root of 2 minus 1, approximately 0.41421, 0.999, and so on without end. Intuitively, there are more real numbers in 0, 1 than there are positive integers. Cantor proved this rigorously using his famous diagonal argument, demonstrating that any supposed complete list of real numbers will always miss some numbers. In other words, the real numbers are uncountable. They are so infinitely numerous that no sequential listing can capture them all. Between any two real numbers, no matter how close, there's always another real number in between, and this property thwarts any attempt to enumerate them without gaps. So we have at least two different infinities, Aleph null, countable infinity, the size of the naturals, and a larger one, often denoted by C, the cardinality of the continuum, the size of the real numbers. In Cantor's terms, C is greater than Aleph null. Another astonishing fact Cantor proved is that the points on a line segment have the same size infinity as the points in an entire plane, or even in an infinite 3D space. So the infinity of real numbers on 0, 1 is the same size as the infinity of points in any finite volume or the whole real line. All are uncountable infinities. This goes against a naive idea that a bigger space would contain more points. Not so in the infinite world. A 1-inch line segment and a 100-mile line segment both contain uncountably infinite points. And in fact, their points can be paired up 1-to-1. Cantor's work revealed a whole hierarchy of infinities. Without getting too deep in the weeds, it turns out you can keep taking an uncountable set, consider the set of all its subsets, its power set, and get an even larger infinity, and do this ad infinitum. There is no largest infinity. There's an endless tower, Aleph null, ALEPH1, ALEPH2, and so on, increasing without bound. Cantor's astonishing 1891 proof showed that no matter what infinity you have, there's always a bigger one. As one source colorfully puts it, Cantor's theorem shows us that the world of infinity is exceedingly rich. There is in fact an infinity of different infinities. The punchline, infinity comes in different sizes. Hilbert's hotel works for the small infinity, countable sets that you can enumerate. But if you had a hotel with rooms labeled by real numbers, an uncountable infinity of rooms, and uncountably many new guests arrived, no amount of shuffling would suffice. You simply cannot list or pair up uncountable guests with uncountable rooms in a sequential way. This limitation is where Hilbert's story reaches its limit in the Britannica explanation. Cantor's discovery that some infinities are bigger than others was one of the most revolutionary and initially shocking results in mathematics. It showed that infinite isn't a monolithic concept. It's a whole universe of possibilities. Our next example is a much more elementary one, but still surprising. An infinite decimal that equals a finite number. when 0.9 repeating equals 1. Can 0.9 repeating, with an endless string of 9s after the decimal, actually be exactly the same as 1? At first glance, it feels like 0.9 repeating should be just a hair less than 1. After all, 0.9 is less than 1. 0.99 is less than 1. 0.999 is less than 1, and so on. It's tempting to think 0.9 repeating is 0.0001 away from 1. However, in the real number system, there is no such thing as 0.0001, an infinitesimal number. That's just 0. In fact, 0.9 repeating is exactly equal to 1, and there are many ways to see this. First, an intuitive argument. Picture the numbers 0.9, 0.99, 0.999, 0.9999, etc. on the number line. Each of these is less than 1. But as you add more 9s, the number gets closer and closer to 1. There is no number between 0.9 repeating and 1 on the number line. They squeeze 1 from below, leaving no gap. Any number less than 1 can be beaten by a sufficiently long string of 9s. For example, if you think 0.999 is below some number, just take 0.9999 with one more 9, and you're even closer to 1. And any number greater than 1 is obviously above all the 0.999 numbers with finite 9s. So if 0.9 repeating were not 1, it would have to be either less than 1 or greater than 1. Both possibilities are logically impossible. The only conclusion is 0.9 repeating equals 1. In brief, 0.999 cannot be bigger than 1 or smaller than 1, so it must equal 1 if it is to be any real number at all. Real numbers don't allow an infinitely small difference between distinct numbers. The completeness property of the real numbers guarantees that an infinite decimal expansion corresponds to a definite limit, in this case 1. If that intuitive argument still leaves you uneasy, here's a simple algebraic proof that is often taught. Let s equals 0.9 repeating, where the 9s go on forever. Then 10s equals 9.9 repeating, multiplying both sides by 10 shifts the decimal point. Now subtract the first equation from the second. 10s minus s equals 9.9 repeating, minus 0.9 repeating. The left side is 9s. On the right side, notice how the infinite tail of 9s cancels out. 9.9 repeating minus 0.9 repeating equals 9.0 repeating, effectively just 9. So we get 9, s equals 9. Divide both sides by 9, yielding s equals 1. Therefore, 0.9 repeating equals 1. Another quick reasoning, 1/3 equals 0.3 repeating, an infinite string of 3s. Multiply both sides of that equation by 3. The left side becomes 1. The right side becomes 0.9 repeating. So 1 equals 0.9 repeating. For those concerned that something fishy is going on, rest assured, this equality is a well-established fact in the real number system, not an approximation or trick. It underscores how infinite processes, in this case, an infinite sum of 9/10 plus 9/100 plus 9/1000, and so on, can yield a precise finite result. Indeed, 0.9 repeating represents the infinite series 9/10 plus 9/100 plus 9/1000, and so on, which is a geometric series that sums exactly to 1. There's no mystery left over. The 0.001-inch difference simply doesn't exist as a real number. Every number has a unique decimal expansion, except those ending in an infinite string of 9s, which tie with another expansion ending in infinite zeros. For instance, 1.000 equals 0.999, or 0.35000 equals 0.34999, etc. So 1 can rightly be thought of as 0.999, just as 0.5 is the same as 0.500 with infinite zeros. This is one of those fun facts that shows up how our notions of almost and exact can collide in the infinite realm. In this case, almost 1 is 1. Zeno's paradoxes. Infinite steps can sum to finite results. Let's shift from numbers to motion and meet Zeno of Elea, a Greek philosopher from the 5th century BC who crafted several famous paradoxes involving infinity. The most famous is Achilles and the tortoise. In this story, the mythical hero Achilles, swift of foot, races a tortoise. Decidedly not swift. Achilles, being sporting, gives the tortoise a head start of, say, 100 meters. Once they start, Achilles runs much faster, let's say 10 times the tortoise's speed, so you'd think he would overtake the tortoise quickly. But Zeno argues otherwise. By the time Achilles reaches the point where the tortoise started, 100 meters mark, the tortoise has moved ahead, perhaps 10 more meters. By the time Achilles reaches that new point, the tortoise has inched further forward again. Achilles keeps having to catch up to where the tortoise just was, only to find the tortoise always a bit ahead. This reasoning can repeat infinitely, suggesting that Achilles can never actually catch the tortoise, because there's an endless series of points Achilles must reach where the tortoise has already left. It sounds absurd. Achilles will obviously overtake the tortoise in reality, yet the argument seems to slice the motion into an infinite sequence of steps that Achilles must complete, with the tortoise always remaining out of reach in those steps. Zeno's paradox highlights a conceptual puzzle. To cover a distance, one must first cover half of it, then cover half of the remainder, then half of that remainder, and so on. There are infinitely many fractions to cover, so how can a finite distance be completed or a race be finished? The resolution, which wasn't fully understood until modern mathematics, specifically the development of calculus and the concept of convergent infinite series in the 17th century, is that an infinite number of diminishing distances can sum to a finite total. Achilles indeed runs an infinite sequence of ever smaller distances in that scenario, but the total distance and total time he takes is finite. For example, Achilles might run 100 meters, then 10 meters, then 1 meters, then 0.1 meters, etc. An infinite series, 100 plus 10 plus 1 plus 0.1 plus 0.01 plus, with each term 1/10 of the previous in this setup. This is a geometric series that converges to 111.111 meters. If Achilles runs 10 times faster than the tortoise, he will cover that approximately 111.11 meters in the same time the tortoise covers approximately 11.11 meters, and that's exactly when Achilles catches up. After that, Achilles zooms ahead. In reality, Achilles does overtake the tortoise, because the infinite process has a finite sum. The paradox is resolved by understanding that infinite does not always mean unending. In effect, you can complete infinitely many tasks in a finite time, as long as each task gets exponentially shorter. This was a profound realization that required the formalism of limits to truly settle. To put it another way, Zeno's argument implicitly assumes that completing an infinite number of steps must take an infinite amount of time. Calculus tells us that's not true if the steps get progressively smaller in just the right way. Motion is not an illusion at all. Rather, the mathematics of infinite sums explains motion nicely. Aristotle and others reasoned that time itself could be divided correspondingly into infinitely many intervals that also get shorter, so the total time can be finite. In our example, Achilles might take 10 seconds to run 100 meters, then 1 second to run the next 10 meters, then 0.1 s for the next 1 meter, etc., totaling 11.11 seconds, a finite time to catch the tortoise. Modern treatments simply sum the geometric series or use the formula for the sum 100 times open parentheses 1 plus 0.1 plus 0.1 to the power of 2 plus, and so on, close parenthesis, equals 100 times 1 divided by 1 minus 0.1 equals 111.11 to get the meeting point, and similarly for time. Zeno formulated other paradoxes too, like the arrow paradox, arguing a flying arrow is motionless at any instant, so how does it move? Or the dichotomy paradox. To go anywhere you must first go halfway, then half of the remaining, etc., implying motion can't even start. These all boil down to misconceptions about infinite subdivision. Today we interpret Zeno's paradoxes as early insights into the concept of limits, and the distinction between an infinite process and its final result. To illustrate the idea of infinite sums more playfully, consider a popular math joke. An infinite number of mathematicians walk into a bar. The first mathematician orders half a beer. The second orders a quarter of a beer. The third orders an eighth of a beer. By now, the bartender is catching on to the pattern. The fourth orders 1/16 of a beer, and so on. The bartender rolls his eyes, pours a single full beer, and says, "Here, you guys can all share this." The joke is that 1/2 plus 1/4 plus 1/8 plus 1/16 plus and so on equals 1. The infinite series converges to exactly one whole beer. The bartender spotted the sum of the infinitely many small orders. The mathematicians, in their nerdy way, were enacting Zeno's dichotomy in the bar. This lighthearted example shows that sometimes an infinite process, adding infinitely many fractions of beer, has a neat, finite outcome. Zeno's paradoxes remind us how tricky infinity can be when mixed with physical intuition. They also underscore the importance of mathematical rigor. You need the right tools, like the concept of a limit, to handle infinite processes correctly. In the end, Achilles wins the race, arrows fly, and the tortoise loses its theoretical edge. The weird rule here is that infinite sequences can converge, a fact that was not obvious until mathematicians like Newton, Leibniz, and others formalized calculus. Fractals and infinite perimeter, finite area. Not all mind-bending infinities come from algebra or motion. Some come from geometry. Fractals are shapes or patterns that display self-similarity at every scale, often leading to infinite complexity within a finite space. One famous fractal, the Koch snowflake, presents a paradoxical property. It has a finite area, but an infinite perimeter. Imagine an equilateral triangle, such as a nice, simple triangle with area equals 1, for reference. Now perform the following iterative process. On each side of the triangle, construct a smaller equilateral bump outward. In the first iteration, the triangle turns into a Star of David-like shape, a 6-pointed star outline. In each subsequent iteration, every line segment gets replaced by a zigzag comprised of 4 segments, creating a little triangular bump on each existing segment. This process is repeated infinitely. Each time, the perimeter becomes more jagged with smaller and smaller teeth, and the shape approaches a snowflake-like curve. This limit shape is the Koch snowflake. What's amazing is how the length and area evolve. Let's break it down. Perimeter. Initially, the triangle has some finite perimeter, say 3 units if each side is 1 unit. Each iteration multiplies the total perimeter by 4/3. Since each line segment of length L is replaced by 4 segments each of length L over 3, making total 4/3 times L for that segment. So after 1 iteration, perimeter equals 3 times 4/3 equals 4. After 2 iterations, it's 4 times 4/3 equals 16/3, approximately 5.33. After n iterations, the perimeter is 3 times open parenthesis 4/3 close parenthesis to the power of n. As n approaches infinity, open parenthesis 4/3 close parenthesis to the power of n grows without bound. In fact, it tends to infinity. So the perimeter of the Koch snowflake diverges to infinity. In the final fractal curve, after infinitely many iterations, the perimeter is infinite, so jagged and crinkly that if you tried to walk around it, you'd walk an infinite distance. Area. On the other hand, the area converges to a finite value. Each iteration adds smaller triangular areas. For our starting triangle of area 1, after 1 iteration the area increases to 1 plus 1/3, because we add 3 little triangles of area 1/9 each on each side. After the next, it adds even smaller bumps, totaling another 1 over 3 squared of area, and so on. The area approaches a limit as n goes to infinity. In fact, the total area turns out to be 8/5 if starting area was 1, which is 1.6 times the original triangle's area. This is a finite number. No matter how many tiny triangles we add, we will never exceed 8/5, approximately 1.6, in area. We just approach it closer and closer. The end result, a finite area enclosed by an infinitely long boundary. The Koch snowflake thus has an infinite perimeter, finite area. You could paint the snowflake shape with a finite amount of paint, since area is finite, but you could never fence its boundary with a finite length of wire. You'd need an infinite amount of fence to go around it. This sounds impossible until you realize the boundary is not a smooth curve but endlessly zigzagging. It never settles into a straight line at any magnification. You see new detail no matter how far you zoom in. The Koch snowflake's boundary is an example of a fractal curve that is nowhere smooth, no well-defined tangent at any point. It's so crumpled that its dimension is between 1 and 2. In fact, the Koch curve has a fractal dimension of about 1.2619. That's why its length can blow up to infinity while the area stays bounded. This counterintuitive situation, infinite perimeter, finite area, is not just a mathematical curiosity. It has a famous parallel in nature known as the coastline paradox. If you try to measure the length of a rugged coastline, say the coastline of Britain, the result depends on the length of your measuring stick. Use a 100 km ruler and you get a certain approximation. Use a 50 km ruler, measuring more nooks and crannies, and you get a larger result. Use a 1 meter ruler, larger still. In the limit, as the measuring scale goes to 0, the measured length of the coastline tends to infinity, essentially because a coastline has fractal-like geometry, with bays, inlets, rocks, etc., adding more length at smaller scales. In short, a coastline doesn't have a well-defined length. The finer you measure, the more detail and length emerges. Real coastlines aren't perfectly self-similar at all scales. Eventually you hit grains of sand, molecules, etc., so they won't truly be infinite, but they can be extremely large relative to the area enclosed, illustrating how fractal geometry breaks the usual link between size and length. The Koch snowflake is one of the earliest fractals studied, described by Helga von Koch in 1904. It was specifically designed to show a curve continuous everywhere, but differentiable nowhere, a shock to mathematicians of the time. It also gives us a neat example of an infinite process yielding a paradoxical result, a finite figure with an infinitely long edge. The weird rule here is that perimeter and area don't have to grow hand in hand. An infinite boundary can bound a finite region. Fractals like this teach us that our Euclidean intuition, bigger perimeter rightwards double arrow bigger area, can fail in the infinite complexity of fractal geometry. The Banach-Tarski paradox, double everything with infinity. Now for a grand finale in the Infinity Hall of Fame, the Banach-Tarski paradox. This is a result so strange that it sounds like a conjuring trick. In plain language, the Banach-Tarski theorem says, take a solid ball, like a solid sphere in 3D. It is possible to split this ball into a finite number of pieces, then reassemble those pieces by simply moving them, rotating and translating in space, to form two solid balls of the exact same size as the original. In other words, you can take one apple, cut it into about 5 pieces, and then put those pieces back together in a different way to get 2 apples each, the size of the first. If your reaction is, that's impossible, it violates conservation of mass/volume, you're in good company. It is impossible in any physical, practical sense. But Banach and Tarski's result, published in 1924, is a theorem of set theoretic geometry relying on the mathematics of infinity and the axiom of choice. The pieces in the decomposition are not ordinary chunks of matter. They are extremely wild, non-measurable sets of points, essentially dusts of points spread out in a complicated way. These pieces do not have a well-defined volume individually. They're not something you could measure with a ruler or scale, so taking them apart and reassembling them circumvents the usual rules of volume conservation. Volume in the sense of Lebesgue measure isn't defined for those sets, so it's not violated when 2 spheres appear. It's not magic or creation of matter. It's a quirk of infinite sets. Let's break it down a bit more. The Banach-Tarski paradox is a direct consequence of 2 things, uncountable infinity and the axiom of choice in set theory. The axiom of choice lets you pick elements from an infinite collection of sets in a certain arbitrary way, and it allows the construction of non-measurable sets, sets that you literally cannot assign a volume to in a consistent way. Using this, one can partition the points of a sphere into 5 subsets with bizarre, fragmented structures. These subsets can then be rotated and moved, without stretching or scaling, to perfectly overlap and form 2 spheres of the same radius as the original. It's as if you had an infinite scatter of points arranged just so that you can regather them in 2 different groups to make 2 identical scatters. It's important to emphasize, Banach-Tarski does not work in the physical world. You can't actually cut a physical sphere made of atoms, say, into a finite number of chunks and reassemble 2 spheres without adding material. Physical chunks are made of finitely many atoms and have well-defined volume. The paradoxical decomposition requires infinitely subdividing points, down to the atomic or subatomic scale and beyond, essentially treating matter as a continuum of points. The pieces are so pathological that they can't exist as rigid bodies, or even definable regions in a lab. They're more like dusts of points, spread out in a specific pattern. Thus, Banach-Tarski doesn't violate conservation of mass or energy in physics. It lives purely in the realm of abstract math. It shows what is mathematically allowed when infinity is in play. The Banach-Tarski paradox highlights the strange rules of infinite sets. It uses the fact that there are different sizes of infinity at play. In a sphere, a 3D continuum of points, there are uncountably infinite points. Banach and Tarski's construction essentially splits an uncountable set, the sphere's points, into a few pieces that each have a certain infinite structure. Then by reassigning those points via rotations, they end up with two uncountable sets of the same size as the original. In one description, they partition the sphere's points into 5 sets, such that 3 of them reassemble into one full sphere and the other 2 reassemble into another sphere. How can 3 pieces make a whole and 2 pieces make a whole? Because each piece is a pretty crazy infinite set of points. Essentially, one lever of the paradox is that a solid ball can be paradoxically equated in cardinality to 2 disjoint copies of itself. After all, both the original and the duplicate have uncountably many points of the continuum cardinality. It's like saying C equals 2C in terms of cardinality, which is true, just as Aleph null equals 2 Aleph null was true for countable sets. Banach Tarski takes that innocent-sounding equation and translates it into geometry with the help of the axiom of choice. This result was so counterintuitive that it prompted deep reflection on the foundations of math. Some mathematicians pointed to it as a reason the axiom of choice is non-constructive or mysterious, since you can't explicitly exhibit the pieces. Their existence is guaranteed, but you can't draw them. Others see it as just a demonstration that our usual notion of volume cannot extend to all sets if we accept choice. Either way, it's a testament to how infinite math can defy finite intuition. While Banach Tarski has no direct physical application, no free lunch or infinite chocolate bars in reality, it stands as a glorious example of the weirdness that infinity permits. It's like a mathematical infinite cloning machine. One sphere becomes 2 without adding anything. Infinity breaks the rules of ordinary arithmetic in a spectacular way here. Effectively, 1 plus 1 equals 1. 1 sphere plus 1 sphere equals 1 sphere in terms of the original's volume. Or if you like, you started with 1 sphere and ended with 2, suggesting 1 equals 2 in terms of that paradoxical decomposition. Hence the tongue-in-cheek description, when 1 plus 1 equals 1. Infinity truly is a different universe with its own rules. As we've seen, the infinite can be full and still have room for more. It comes in countless sizes. It can turn almost into exactly. It allows infinite processes to sum up neatly. It creates shapes that blur the line between dimensions, and it can even produce outcomes that look like cheating, doubling a ball, when viewed through a finite lens. Each of our topics, Hilbert's hotel, Cantor's infinities, 0.9 repeating equals 1, Zeno's paradoxes, fractal snowflakes, Banach Tarski, showcases a different facet of infinity's weirdness. And yet, underlying each is a rigorous mathematical truth. These examples aren't logical loopholes. They are legitimate results that have been carefully proven, often after initially perplexing the experts. Why do we say infinity is real? Not necessarily because you can point to an infinite object in the physical world. Whether the universe is infinite in size or time is still an open question for cosmologists. We say it because, within mathematics, infinity is as real as it gets. It's a concept we can reason about, wield, and that yields very real, if surprising, conclusions. Understanding how infinity works allows us to avoid paradoxes in calculus, so Achilles can finish his race, to know the deep structure of numbers, so we accept 0.999 equals 1 and don't find contradictions, and to push the boundaries of math, exploring set theory, geometry, and logic. David Hilbert, who gave us the infinite hotel analogy, had a quote about infinity. The infinite is nowhere to be found in reality. It neither exists in nature nor provides a legitimate basis for rational thought. The role that remains for the infinite to play is solely that of an idea. Indeed, infinity is an idea that transcends all experience and lets us conceptualize the boundless. Yet through these thought experiments and paradoxes, we see that this idea has very concrete rules and consequences. It's an idea that has expanded our minds, showing that the universe, mathematical and perhaps physical, doesn't have to abide by the limitations of the finite. Infinity, in all its forms, invites us to marvel at how something can be unending and untamed, yet follow strict principles. It teaches us humility, that our everyday intuition is a poor guide in the infinite realm, and it inspires wonder as we glimpse the weird rules that govern the endless. For math enthusiasts, these paradoxes and properties of infinity are a playground of the mind, a place where you can check into a full hotel and still get a room, where numbers beyond counting exist, where 0.999 lives a double life as 1, where a foot race involves summing an infinity of fractions, where a snowflake's outline never straightens out, and where you can seemingly get something from nothing, but only because you had infinite something to start with. The infinite universe is indeed weird, and that's what makes it so fascinating. In exploring these examples, we've seen that infinity is real, not in a physical sense, but as a vital part of mathematics that yields real insights and delightful puzzles. Embracing the strange rules of infinity expands our understanding of what's possible, and reminds us that in the realm of the infinite, our only limits are the ones we imagine.